Welcome to this lecture. This lecture is somewhere in the second last lecture of this particular course, and we have reached to the point that we have seen somewhere from ICs to MOSFETs followed by the op amps and their application. The idea is also that when you are given a data sheet, can you open the data sheet and can you see what are the parameters given in the data sheet, and can you understand what are the parameters, right. So, I thought of how we go through the data sheet and let us see what are the parameters given and whether we understand those parameters, whether we can solve some equations, solve some problems regarding to that particular parameters, right. So, for this particular lecture we will be looking at the data sheet of IC 741 which is from Fairchild, and then we will see some of the parameters in the presentation slide. Alright. So, if you see the screen shows the data sheet for RM 741. It is also called single op amp or single operational amplifier. So, what are the features of the single operation amplifier? Features are short circuit protection, excellent temperature stability, internal frequency compensation, high input voltage range and null of offset, right. These are the features of this particular IC. Now, if we look at the description, what we see that LM741 are general purpose op amp. It is intended for wide range of applications, analog applications, high gain and wide range of operating voltage, provide superior performance as an integrator, summer or as a general feedback applications, right. So, these are all the parameters in the data sheet, but not all the parameters, this is just first slide of the data sheet. In fact, you see that there are two ICs, one is dual inline package DIP, another one is SOP, it is 8 pin because the op amp has the 8 pin that we are learning until now, right. So, if I move to the next slide, what we see, we can see the internal block diagram of the IC as we have learned in our earlier classes, right. 2 is inverting, 3 is non-inverting, 6 is output, 7 is VCC, 4 is VEE or minus VCC, between 1 and 5 we can have offset null, between 1 and 5 we can have offset null, sorry, and 8 is not connected, right. So, this is our IC, these are internal block diagram. If you further go in, you will see the schematic diagram where you can see the offset and null. You can see here where is the inverting, where is the non-inverting terminal, how the output is taken, and like I said, it has a 4 different blocks from input to output to understand the op amp, right. Now, we do not worry about it because that is another part where you can understand or you can learn how to design the circuit, how to design this particular internal circuit of the operation amplifier. That is not the idea of this particular course, okay. But anyway, those who are interested can learn cadence. Cadence is used to design this circuit diagrams or the internal circuit of the amplifiers and lot more. So, when we look at the absolute maximum ratings at 25 degree centigrade, what we see? Supply voltage, right, VCC, we have seen that, differential input voltage, input voltage or output short circuit duration, power dissipation, temperature range and then short temperature range. So, we see these parameters as absolute maximum ratings. Then what we see? Then we see electrical characteristics. Okay. So, the things that we are looking here in this particular slide, we will also see some of those, how we can actually solve the problems using this particular for this particular parameters. Okay. So, now you have parameter which is input offset voltage, you have input offset voltage adjustment range, then you have input offset current, then you have input bias current. We have seen this, right, we have also seen the problems using input offset current, input bias current, input offset voltage, right. Then there is input resistance followed by input voltage range, large signal voltage gain, output short circuit current, output voltage swing. See, so many parameters are there, right. Then we go further, common mode rejection ratio, some of the parameter you will immediately recall because we have already discussed, right. Common mode rejection ratio, there is another called power supply rejection ratio. Then bandwidth, right, slew rate, supply current, power consumption. So, it should not come to you as suddenly something that you do not even know, right. We have seen that common mode rejection ratio is given in decibels, we have seen that the bandwidth is given in megahertz, we have seen that the slew rate is generally given as volts per microsecond, right, power consumption is generally in millivolts. So, we know these things, right. Okay. If we go further, if you go further, what we see? Typical performance characteristics, right, output resistance versus frequency, then we see input resistance versus input capacitance versus frequency, we see input bias current versus ambient temperature, we see power consumption versus ambient temperature. These are performance parameter of the op amp, alright. So, when we look at this plots, we will understand with temperature from -20 to 60 how the input resistance will change, how the input resistance will change. With respect to the temperature, how your input offset current and input bias current would change, right. With respect to frequency, how your output resistance is going to change. With respect to your frequency, how input resistance is going to change, right. So, these are the plots. Then there are another plot called input offset voltage versus ambient temperature, how input offset current changes with ambient temperature. We have then we have how the input resistance changes with the ambient temperature, right. Then we have normalized DC parameters versus ambient temperature. For example, input resistance, power supply current, output short circuit current. Then we have transient response, frequency characteristics versus ambient temperature, transient response, slew rate, closed loop bandwidth. Then we also have output short circuit current versus ambient temperature. We also see there is a slew rate, transient response for frequency characteristics versus supply voltage. So, lot of plots are there that we need to understand. Transient response, right, we can see here common mode rejection ratio versus frequency. So, what we also understand is that apart from this particular parameters, there are other parameters which are called mechanical dimensions, right, how the packaging is done. For example, 8 pin Deon inline package, right, what is the size of this pin, what is the size of the chip, what is the size of this IC, right, everything is given, you see the spacing between 2 pins, the size of each pin, right, the length, everything is given in the data sheet. If we go further, for SOP also everything is given, right. So, ordering information, right. So, if you want to use temperature from 0 to 70, we can either have LM741 8 pin DIP or 8 pin SOP, while if you want to go from -40 to 85 degree, we have to go for 8 pin DIP LM741 IN. Alright, this is the ordering information. When you want to order a IC, you should know what parameters you have to use. You will know this parameter when you look at the data sheet. When you understand the data sheet, then you can understand which IC I should order, right. So, to the ordering information is also given, as you can see here, right, from the temperature point of view, from the operating temperature point of view, but there are other parameters also. So, like we have discussed earlier, which are the input bias current, right, temperature compensation, power supply rejection ratio, common mode rejection ratio, input offset voltage, CMRR, right, common mode rejection ratio. Then we have what is the operating frequency, how the input resistance would change, how the output resistance will behave with respect to ambient temperature, how things will behave, right. So, these are all the things that you have to understand when you are looking at the IC. Alright. Now, since we have seen what the data sheet generally gives us, right, this is the end of the data sheet, as you can see here. What data sheet gives us is this particular parameters, right, including the mechanical dimensions, including the electrical characteristics, right, several plots, right, like I said, including electrical characteristics, right. Then we should understand how each thing helps us to understand for the design of the circuit. For example, input offset voltage, why we need to understand input offset voltage, why we need to understand input voltage drift, why we need to understand input offset current. So, let us see what are these parameter and how we can design the circuit, or how this will affect the overall performance of the circuit. Okay. So, to understand that which is understanding the op amp characteristics. Okay. So, let us understand how the input bias currents affect the amplifier operation. We will see few of the parameters and we will see how they are affecting the operation. Okay. So, first one is input bias current IB1 and IB2. We have seen in the lectures what are input bias current. Let us quickly once again see. Ideally we know that input impedance of op amp is infinite, right. Then there is no current entering the input of the op amp. But in the real world some current does enter the inputs. In practical op amps we see that there is some flow of current. This amount of current that flows into the input pins of the bias transistor are called input bias currents, that are called input bias currents. Typically the range is 80 nanoampere in case of 741, alright. Now some FET op amps have input bias current well below 1 picoampere. Okay. The op amp data sheet usually specifies, see we have seen the data sheet, it has input bias current as the average value of input bias currents IB1 at non-inverting terminal and IB2 at inverting terminal. So, the data sheet when we say it will show you the IB value which is nothing but IB1 plus IB2 by 2, right. We have seen IB equal to IB1 plus IB2 by 2, correct, we have seen in earlier lectures. So, this is your input bias current, input bias current. Now to understand the effect of bias currents on the op amp, let us consider inverting configuration as shown in the figure here, right. So, what we see, if we apply, if this is R1 R2, this is an inverting amplifier as you can see very clearly, right. So, if I apply a KCL, that is Kirchhoff current law, at node A here, okay, what I see, I1 equals to nothing but I1 equals to I2 plus IB1, right, I1 equals to I2 plus IB1. If I apply virtual ground, what I will find? I find that V minus equals to V plus, because this is grounded, your inverting terminal is grounded, that is why I can think that the V minus will be equal to V plus equals to 0, right. The voltage at the inverting terminal will be same as the voltage at the non-inverting terminal, and since the non-inverting terminal is at ground potential, so it has 0 voltage, the V minus will also have 0, that is a V minus equals to V plus equals to 0. Therefore, from Kirchhoff voltage law and Ohm's law, what we find as I in or I1, right, I1, this one I1 equals to nothing but V in minus V minus by R1, right. I1, if you see this one, this current, what is it? V in, and we have to consider V minus, right. So, V in minus V minus divided by R1. What is V minus? V minus is 0. So, this is nothing but V in by R1, right. Similarly, if I want to derive I2, then what is the case? I2 equals to this is I2, right. I2 is equals to nothing but you have to consider this and this. So, V minus, right, V minus V out divided by R2. This will give us nothing but minus V out by R2. Got it? So, I2 is nothing but minus V out by R2. Now, we know what is I1, we know what is I2. So, combining both the results, we can say V in by R1 equals to V out by R2 plus IB1, right, because IB1 is flowing here, correct. Now, output voltage would be V out equals to minus R2 by R1 into V in plus R2 IB1 plus R2 IB1, right. So, note that if IB1 equals to 0, the result reduces to the expected inverting amplifier equation. So, what is the expected inverting amplifier equation? Expected inverting amplifier equation is V out equals to minus R2 by R1 into V in, this is our expected output, right. But if IB is not equals to 0, then we have to consider V out equals to minus R2 by R1 V in plus R2 into IB1, right. So, the results reduced to expected inverting amplifier equation, and second term in the above expression IB1 R2 represents the offset voltage, output offset voltage. You got it. So, this is very important, right. This is very important. Why output of offset voltage? Because this much amount of voltage we have to adjust to get the output equals to 0 when I have to balance my amplifier, not ground, output equals to 0, then I have to adjust my output. So, it can be analyzed that if input is not connected, V in equals to 0 and ideally V out equals to 0, but because of input bias current there is an output voltage even at 0 input. Now, you guys understood that if I ground both the terminals V in also with respect to V plus, then also I will see that my output voltage is not 0, but I will find some amount of voltage, that voltage is due to the input bias current. Now, you got it. Why that voltage is there? That voltage is due to the input bias current, right, and a typical bias current of op amp is nothing but 80 nanoampere. It results that when no input voltage, that is V in equals to 0 and op amp has a feedback resistance of 1 mega ohm, the op amp will produce an output voltage of V out equals to 80 nanoampere into 1 mega ohm, which is nothing but 80 millivolts. Okay. Now, in application where the signal levels are measured in millivolts, this is totally not acceptable. This can be compensated. So, for example, if I use a op amp for designing a signal conditioning circuit for a sensor, even when no stimulus exists, it results in an output voltage, correct. That what does this mean? What does the above sentences means? That when I have input voltages equal to 0, I see that there is a presence of output voltage, and this voltage causes some amount of current, and these levels are measured in millivolts, right, but these millivolts are there, this output voltage of millivolts is there even when there is no input voltage. So, suppose I connect a sensor here, right, let us say this is a sensor, then without applying any stimulus to the sensor, the output voltage we are getting some kind of output voltage, right. When the sensor changes its value, the output should change, but when I am not using the sensor at all, the output should be 0. But I see that there is a resultant output voltage. The system may understand that stimulus exists, generally sensitivity of sensor is very poor and hence it affects the accuracy of the system, right. So, this is an example how the input bias current affects the overall performance of the amplifier, right. So, now the question is, if that is the case, we have to compensate the effect of input bias current, right. How to compensate the effect of input bias current, that is a question. So, it can be seen from the output voltage expression that one way to decrease the output offset voltage is by minimizing the feedback resistor R2, but decreasing the feedback resistor R2, the required gain cannot be achieved, right. So, why? So, what is the formula? If you see the formula was V out equals to minus R2 by R1 V in plus R2 into IB1. So, if I say, if I reduce this value R2, right, if I reduce value of R2, then I will have minimum effect of IB1, right, minimum effect of my bias current, but this will also affect my gain. Because I cannot have R2 too small, otherwise I cannot have amplification, right. So, this is not a possibility. So, one way to compensate the effect due to bias current is by using a resistance at the non-inverting terminal to the ground of an op amp. Okay. So, what is the answer? Answer is that we can use a resistor at the non-inverting terminal of the op amp. So, how does it is helpful? How it is helpful if I attach a resistor at the non-inverting terminal? So, see what resistance to be used, right. To know what resistance is to use, let us consider the figure below, which you can see here, right, where the input is also grounded and non-inverting terminal is connected with resistor R3, right. So, input is grounded, you can see here ground, you can see here ground, right, and then you can see here resistor R3. So, applying KCL at node A, here Kirchhoff current at node A, what I get? I get is nothing but I1 equals to I2, right, plus IB minus, right. So, applying virtual ground concept, IB plus here equals to 0 minus V plus divided by R3, correct, which is V plus equals to V minus equals to minus IB plus R3, minus IB plus into R3, right. So, therefore, from Kirchhoff Ohm's law what we get? I1 equals to V in minus V minus divided by R1, or 0 minus what is V minus? V minus is nothing but minus IB plus into R3, right. This will give me IB plus IB plus into R3 by R1, R3 by R1. Now, if I have this equation, what will my I2? I2 would be nothing but I minus IB plus into R3 minus 0 divided by R2, right. What will be IB I2? I2 will be would be minus IB plus, right, minus IB plus into R3, right, minus V0, right. So, minus 0 divided by R2 equals to minus IB plus into R3 divided by R2, right, because our interest is to make output 0. So, on substitution what we will have? We have this particular equation, right, as you can see here. From there we can have value of R3 by R1, and finally we can have what is the value of R3? R3 would be nothing but R1 parallel to R2. So, now if I have an amplifier, inverting amplifier, right, if I have an inverting amplifier and if I know the value of R2, if I know the value of R1, from that I can decide what should be the value of R3 such that my output voltage would be 0 when both the input are at ground terminal, right. So, from the above analysis we can understand that by adding a resistor at non-inverting terminal of the of R1 parallel to R2, the effect due to the bias current can be neglected. Got it? Easy. Now, we understand, okay, input bias current is there, but if I want to remove the effect, or if I want to minimize the effect of the input bias current in an amplifier, this is how I can minimize the effect. For you directly you can understand, just by keeping R3 equals to R1 parallel to R2, we can solve the issue of input bias current. Easy, super easy, right. So, if I know what is input bias current, and then if I know that if I want to use an amplifier, that is inverting amplifier, then I know that there is a value of R2 feedback resistor, input resistor R1, then I will have a value of R3 which I can connect between non-inverting terminal and ground, and that value of R3 would be equal to R1 parallel to R2. Thus, I am compensating, or I am removing any effect of input bias current on the output of the amplifier, right. So, this is a way how you can understand the input bias current. Okay. So, this is end of this particular module. In the next module, let us see what is the effect of input offset current. So, right now what we have seen effect of input bias current. In next module, let us see what is the effect of input offset current. Alright. Till then, you take care and just look at the lecture. I will see you in the next module.